Okay, so last week we started talking about sensation, and we started really from the physics of the world. We started from the environment. We talked about what energies are out there, which one of these energies becomes vision, and we kind of started from talking about the light leaving the sun and like hitting a surface and then reflecting from that surface into your eye. And then what happens in the eye, we talked a little bit about it, but we're going to continue that journey. Like we're gonna continue to look at what happens to light as it enters the eye, and then as it goes on and enters the brain. Um, so last week we left off talking about the architecture of the eye, and what makes it somewhat peculiar was the fact that the photoreceptors are inside this coating that we call retina at the back of the eye. And we were saying an alternative would have been if these photoreceptors were on the outer layer of this coating, so the light, when it travels through the lens, hits them directly. But in the eye, they happen to be on the inside, like the inner part of this coating. So what happens is that the light has to travel through ganglion cells and middle layer cells in order to hit the photoreceptors. And one complication from that structure is that all these nerves, these axons that are leaving the ganglion cells, have to leave the eye at some point. So the eye, they would create a hole in the retina where there are no photoreceptors. There are only nerve cells. And in this part of the eye, there is no sensation of the light out there, and that's a blind spot that we talked about. So another thing about the eye that is very important is the distribution of photoreceptors. There are two types of photoreceptors in the eye, rods and cones, and their distribution is very different. When you move near the fovea, and the fovea is the point that we talked about. This is the point where your central vision is. This is the point when we're looking at something, the light reflecting from that object would project up to this point, and we call that the fovea, which is a small area in the retina. When you move near fovea, you're going to have a lot more cones, which are these shown in red here. And when you move away from the fovea in the retina, you're going to have a lot more rods. Cones and rods look different. This is how they actually look like under a microscope. A cone would look like this, rods would look like this. So this is the schematics inspired by the real shape under a microscope. This is how the distribution looks like. So let's work through this. 0 is from, that's where the fovea is. Let's say this is 0 angle. Like we measure a lot of things in the world as visual angles. So you can imagine that the whole world is 360 and then you have 180. The suggestion here is that you really have what? Maybe plus 80 to minus 80, right? If it was 90 to 90, it would be the entire hemifield, right? It would be the entire front of me. But it's around maybe 70 for a lot of people. So you're starting from a center, 70 degree to the right, 70, that's your visual field. And you could project that onto the retina. You could basically say, well, this is the 0 degree, everything that is like a few degrees is here and all the way up to, and we'll show how the projection happens. But so the distribution of cones is shown in the dark color, and the distribution of rods is shown in the well, in the MTS or white color here. What you see here is that in the retina, in the fovea, there is a large peak in the number of cones, in the density of cones, and there's almost no rods there. As you go into the periphery, you're going to have a lot more rods and very few cones. and there is a blind spot where there are no photoreceptors. That's where the axons are leaving the eye. So most cones are in the fovea that constitute central vision. Most rods are in the peripheral. Rods and cones have different properties, and those properties define what we call central vision versus peripheral vision. For example, one thing that's very different between them is in their convergence factor. Now, convergence factor is something that we talked about before. When something has a high convergence factor, when a cell has a high convergence factor, it means that it's averaging information from a large part of the world. What is the result of that? The result that the response of the cell cannot be very specific, meaning that I'm going to show you in the context of neural computation what that would mean. So let's take this cell B here, but I want it to be one word. Okay, let's take cell B here, and you've seen this graph, you worked with them, and you studied them for your exam. As you can see, all the connections here are excitatory. If I have a pattern of light that lights up 1, 2, 3, 6, 7, versus a pattern of light that lights up 1, 2, 4, 6, 7, would the B respond differently to those patterns? So let's say one pattern of light is 1, 2, 3, 6, 7. Another pattern of light is 1, 2, 4, 6, 7. It wouldn't respond differently, right? It would be the same because the amount of excitation that you're getting is the same. But what does that mean for the response of cell B? It means that it is not able to differentiate between these two patterns. Does that make sense? So in a way, when we're saying you're averaging a lot of information, you're not responding differently to all those different patterns of light that you could get. Those different patterns of light could be different letters in the alphabet, because those are basically just different patterns of like visual input is different patterns of light. When you have a high convergence factor, if you're in a busy room, multiple people are talking, and you're kind of averaging all you're not going to be distinguishing what they're saying so well. You have a general response to your surrounding, but you're not able to distinguish them. So you work with these networks and you're kind of comfortable with them. So that's a good thing. Okay. In this context, if I say rods have a large convergence factor to ganglion cells, it means that a large response of a response of a large number of rod cells is being averaged out to go to a ganglion cell. When I say cones have a low convergence factor, it means that every cone or very few cones are connected to one ganglion cell. So what would that mean for the response of a ganglion cell that is connected to cones? Well, they would have a very different response to a visual input. Imagine this is your visual input versus this visual input. If you move this a little bit, the response of a ganglion cell would not be different, like the way I described the pattern of light, because you're averaging out a lot of response. In the fovea, that's different. In the fovea, you have a low convergence factor. So when you have a low convergence factor, you could maintain the details of the input as you project this information to the rest of the brain. That's what that means. I'll explain that a little more later. So what are the differences between rods and cones? They're distributed differently in the retina. The fovea contains only cones. The peripheral retina contains rods and cones, but mainly rods. Rods and cones are wired differently to the ganglion cells that I just described. Many rods connect to one ganglion cell, but cones are almost one-to-one. Rods operate under dim lighting condition, cones operate under brighter lighting condition. So photopic vision, which is day vision, it's mediated by cones. Scotopic vision, night vision is mediated by rods. So let's go, I'll go through these things. But if I tell you that in order to have color vision, you need cones. Like if someone doesn't have cones, they don't have color vision. What does that tell you about the properties of these photoreceptors?
They capture the wave.
What does that mean? They capture the wave? What does it mean to capture the frequency of the light? You're on the right track, but I want you to elaborate on that. When we say they capture the frequency of the wavelength, frequency or the wavelength.
They're sensible to frequencies and the vision, visible light.
Yeah.
They can register and they are they're activated. Like there's a receptive fields for visible light.
So that means that cones can differentiate the response within the range of the visible light, right? If you want to perceive something, there has to be a differentiating response to them. If you respond to things similarly, then you cannot differentiate them, right? So this is true in the retina and this is true in the brain. If all perceptions and sensations are these patterns of activation, when you have two different perceptions, that must mean that the patterns of activation are different. Does that make sense to everyone? So if you're looking at one face and you're perceiving that face, you're looking at a different face, you're perceiving that face, and the faces are two different faces and you're perceiving them as two different faces, that must mean that the pattern of activation that is in your brain is different. Right? There's no way. If you have the same spatial temporal pattern of neural activity in response to two stimulus, you cannot have a different perception of the two stimulus. Does that make sense to everyone? This is an important point. If cones can mediate color vision, it means that cones are responding differently to different wavelengths of light within the visible range. When rods cannot differentiate between them, it means that they're just non-color vision, right? Rods can only respond to the presence of visible light or not. They cannot differentiate. If there is not photoreceptors that respond differently to different frequencies of light in the visible range, you're not going to be perceiving colors, right? So it's important to understand that you have to have senses that are sensing things differently for you to be able to perceive them. So again, that's a bigger point that is important. It's going to come up in that all perceptions are a distinction, right? Everything that you're perceiving is a distinction of neural activity, and that has to be different for another perception. So rods, as we said, they mediate peripheral vision because they're all mostly in the periphery. There is none in the foveal vision. There are many more of them, around 120 million of them compared to cones. They have poor spatial resolution. What does that mean? Yeah? Yeah, so less ability to differentiate fine details, right? So when you take a picture and the picture is blurry, what information do you lose? Okay, so you lose details, right? You don't lose necessarily pixels or the edges become less. So if the edges are small or detailed, you lose that information, right? So when something is blurry, we say that it's low spatial resolution. And that low spatial resolution lacks details. And that's what rods give you. And the reason they give you that is why? Yeah, so if you take an image, if you take a photo and apply an averaging on it, an averaging is just take a box, put it on the image and average like a 5x5 window of pixels. And then just move that. What you're doing is that you're just averaging. What's going to happen to that image? Does anyone know what happens if I do that operation on an image on every pixel? What's going to happen to it? It gets blurry. If you take an image and put a window of, let's say, 5 by 5 grid on it, and average all the values and put in that pixel, then move forward, average the value, put it in that pixel, that's called a low-pass filter. That's what it's called in signal detection, right? A low-pass filter gets rid of high-frequency details. You're just getting blurry stuff. So when you look at a blurry image, you're losing a lot of high-frequency details, and what you're left with are these more bigger changes in the image. So it has a poor spatial resolution because it's converged. A lot of responses are being converged. It's much more light sensitive. The photoreceptors rods are much more light sensitive than cones. They function in dim light and they're achromatic. They're not color sensitive. When like a lot of night vision is mediated by rods, like we're much better at detecting very dim light in the periphery than we are in the central vision. So if we want to detect a really dim light, your periphery is much better. Like it's best not to look at it when you want to detect a very dim light. Cones mediate central vision, which is the foveal vision. There are 5 to 8 million of them. They have very good spatial resolution. They're not losing any details because they're not doing any averaging. They're less light sensitive. They function in daylight and they mediate color vision. So, any questions about cones and rods? No? Okay. So, we're going to talk about now what is exactly transduction. What really happens when you have the light energy becoming neural activity. So as I mentioned many times, the brain can only work with neural activity. It cannot work with physical energies in the world. So the first step in cognition is sensation. You have to turn the physical energy in the world into neural activity. In this case, it happens using photopigments, right? Photopigments are in these photoreceptors. There are many of them packed in a photoreceptor. And what they are, they really just proteins that are somewhat unstable. When a photon of light hits them, they change shape. When the pigment changes shape, it opens ion channels. And the ion channels, do I have the description there? Yeah. All right. So the photopigment in the rods is called rhodopsin. And when a photon of light hits the rhodopsin, causes rhodopsin to change its shape. This causes receptor sites to open, and it results in hyperpolarization. Okay, so when I say it results in hyperpolarization, what is the effect of it on the neural activity of the photoreceptor? We took an exam on this. Yeah. So it brings the neural activity of the photoreceptor down. The photoreceptor happens to have an inhibitory connection to the middle layer cells. What is the net effect of this process on the middle layer cells? Okay. So what is the effect on this firing rate? The firing rate would go up. So what is so again, you take an exam on this, so you kind of have a mental model of it. Photoreceptors have a baseline activity. This baseline activity is inhibitory. It has inhibitory connection to middle layer cells. It means that it's constantly releasing inhibitory neurotransmitters for middle layer cells. So generally, the photoreceptors at a baseline activity are inhibiting the middle layer cells because they're constantly releasing inhibitory neurotransmitters. Light makes photoreceptors hyperpolarize. So it brings down the activity of photoreceptors. So when the activity of photoreceptors come down, what does it mean for the inhibitory neurotransmitters that it's releasing? Is it decreases? the inhibitory neurotransmitters decreases, the result is that the activity of middle layer go up. Does that make sense to everyone? So you kind of work with these networks. So this is kind of a double negative because, well, it was inhibiting. I don't want to put you through the metaphor again, but the idea is that you're picking your foot off the brake pedal or something like that in those 4 conditions that we had. But think of it in terms of neurotransmitters. When I say photoreceptors have an inhibitory connection to the middle layer cells, it means that they're constantly inhibiting the middle layer cells. If they're constantly inhibiting, it means that they're constantly releasing inhibitory neurotransmitters. Now, if you bring down the activity of photoreceptor, the density of these inhibitory neurotransmitters is going to go down because they're not releasing them as much because they're not as active. And because that goes down, the next layer level goes up, right? So it's not that, well, light activates something and that's the activity. No, it actually goes through this process of inhibiting the photoreceptors, and the inhibition of photoreceptors seesaws and increases the next layer activity. That is sensory transduction. That's how light becomes neural activity, right? Through this process. Everyone's comfortable with how light becomes neural activity? Yeah, so there are a lot of these photopigments in the receptors, and then they respond to it, and then after the light goes away, they regenerate, and that the cycle goes on. Okay. So that's about the density of cones and rods and how they behave. Another thing that is interesting about this structure of the eye is that there's a dip here where the fovea is, and they call this the foveal dip. Why would this dip be there? Why would there be a dip at the fovea in the retina? Looking at this structure of the connectivity, again, everything has its roots in connectivity, right? I think I try to make this point over and over because it's important. Connectivity tells you about function, and connectivity tells you what consequences there will be. Yes. It's what? It is the focal point of the lens, but why would there be a dip? The dip is really the parting of the cells. So what's happening here is that the light has to travel through all these cell bodies to get to the photoreceptors. But you really care about this high resolution information that you get at the fovea. So you want to minimize the scattering of light that would happen when it hits these cell bodies. So the solution that the brain has found, or the evolution has found, is to part these cells from each other at the point of fovea. So you take all these cells and then push them aside in order for the light to go directly hit the photoreceptors, the cones that are located at the foveal location, so the light is not scattered. Does that make sense? So you don't want to lose the high resolution information of the light by scattering it, and that's why there's a foveal dip or a pit. So fovea is important for all those reasons that I just mentioned. As you mentioned, fovea is really this focal point of this lens, and it's at the optical axis. There's a lens in the eye that bends light, and when there is an optical axis, the optical axis is the ray of light that does not get bent at all, right? It does not get distorted at all. If you play with a lens generally bend the light in order to focus it at their focal point. But if you are at the optical axis, it doesn't get bent at all. And that's a great thing because again, it goes to the fovea, so you're not bending the light at the lens and you're not really distorting it by the cell bodies, and you have all the cones packed here, so fovea maintains really good spatial resolution. And the other way of saying really high spatial resolution is to say it has a very high visual acuity. It's just really the same thing. Okay. Okay. Any questions so far? No, everything's clear? Super clear for everyone? Yeah.
How the indent of the, I don't know, I just don't fully understand how it works. Like, why does the carding?
So I guess it all comes from the fact that, as I was saying, photoreceptors are on this side of the retina. The light comes from this direction. And all of these layers that you see here, these are cells. And the photoreceptors, because they're on this side, it means that the light has to go through these cell bodies, as you see here, this is light, and it's traveling this way. It has to go through these cell bodies in order to reach the photoreceptors. Cell bodies, they're solid and they scatter light. When the light comes through them, it hits these cell bodies, it gets scattered. But for the fovea, you would ideally want light not to get scattered when it hits there, because you don't want to lose information. And this parting ways of these cells allows the light to travel to the photoreceptors without getting scattered. Yeah? Make sense or no?
It does make sense, I suppose, just like,
For that reason. Just because, again, because of, so I was saying the structure, because the structure are like this, so for the same reason the blind spot exists. These are not supposedly intelligent designs, right? These are, it's a product of evolution, and evolution, when it finds a good enough solution, sometimes you get stuck in it, right? In life, we also, when we have a good enough solution, we get stuck in it. We don't search for much better solution. And this is one of those examples where you have a good enough solution where the photoreceptors are getting the light. It's not ideal, but the fact that you create a hole in the retina is another example of a consequence of this architecture, and also creating a dip here, physically visible under a microscope. If you look at a microscope, the fovea, you could see where the fovea is by the fact that there's a pit there where the cell bodies are parting ways. Again, it's a good enough solution, but the problem is about it is that, as I said, the photoreceptors are on this end, so all these nerve endings have to leave the eye somewhere. That creates a blind spot, but also they scatter light, so light doesn't get directly to the photoreceptors. Does that make sense? Okay, so let me spend a few minutes on the lens itself. So there is, as I've been saying, there's a lens in the eye. It's right, so this is the front of the eye, right? The pupil, and the lens is sitting right here. And this lens is not completely solid, right? You could actually, the muscles could actually move the lens. Why would you want to do that? Does anyone have a camera or something? Why would you want to do that? Yeah. Yeah, so if I want to look at something, if I want to read something in front of me, or whether look at a face in the back or read that sign in the back, I have to change, I have to do a lot of these changing of the shape of this lens in order to focus at different things at different distances. I can't be able, you can't just have a solid, because what you're doing is that you're taking the light and then you're focusing it on your fovea, and you need that to be able, so you may know certain, element of the eye is that this thing gets hardened and you cannot move it as much. So there is a lens, and the lens job is a lot of time to focus the input, the visual input, in order for you to be able to see it in all details. But what lenses do is that they flip the light, right? If you ever, again, played with a lens, you know that when the input comes, it gets flipped horizontally and vertically. So in this case, when you're looking at this, like peepholes have this property too. When you're looking at this pen, what happens is that the pen gets inverted on the retina. Where the top of the band, the light that is coming from this area gets projected on this side of the eye, on the retina, and then this side on that side. And you could see again the fovea here, the pit is there, the blind spot, the optic nerves leaving the eye. This is an important feature, and when it also does this flipping horizontally. So what is the consequence of that? When you flip something horizontally, what is the consequence of that in the brain that you know about? You've heard that like the left side of the brain, for example, processes information from the right side of the world, right? And this is the reason for that. For a large reason for that is having this lens, and we're going to talk about it. But that comes from the eye. It starts from the eye, and the fact that the eye has this flipping of the visual input, and then it gets propagated into the brain. I think this is all I wanted to say here, really. Yep. Any questions? Yeah.
So you're saying that it flips because like the lobes of the brain are switched, or
No, I'm not saying, I'm going to talk about why you process one side of the visual field in one brain hemisphere. Not because they're switched, it's just because the information gets there. I'll talk about it right now. Any other questions before we get into it? If you're not asking questions, I assume that this is all clear and you're understanding everything, okay? So let's look at what happens when you have visual input into the eye. This is the right eye, left eye. This is the back of the brain, right? This is the front because the eyes are there, and this is the back of the brain. This is where the nose would be, and this is a slice of the brain this way, right? So take the eye and then slice back, and then you're looking at it from the top, right? You all have you see how this is shown. So when you're looking at the world, you have the right visual field. Anywhere to the right of my fixation is the right visual field. Anywhere to the left of it is the left visual field. So how does this projection happen? If there is a lens here, the right visual field would go and project. And you see these, and you can imagine this is where the blind spot is. This is where the nerve endings are leaving the eye and going to the brain. So the right visual field, shown in green, would project on this side of the right eye. I'm standing here, this is my right eye. That side of the world gets flipped and projects into the right side of the left side of the right eye. And we call that the nasal side because it's close to the nose, right? Just keep it, just imagine it that way. What happens when it projects to the left eye? So if it projects into the left eye, it would project to the temporal side, which is the other side, right? There's a nasal side and a temporal side. Do you all see why the right visual field projects to the left of the blind spot in both of these, right? So these nerve endings are leaving the eye, but they're not mixed. When they're leaving the eye, the nasal part of the right eye and the temporal side of the left eye are leaving the two eyes, and then somewhere that is called the optic chiasm, they actually cross over. The one from the right side crosses over and goes to the left side of the brain. So what is the result of this? The result of this is that all the visual input that is coming from the right visual field is going to the left hemisphere in the brain. Yeah?
Point, is the image flipped, like in the process of like light coming in, it comes into the eye, it's flipped vertically and horizontally, and then when does our brain flip it back?
I don't think there's a place where it flips back. So it's a more philosophical problem, right? In a sense that you don't have to flip it back, right? It's what's vertical and what's, I guess, what's upright or not is in the eye of the beholder. So meaning that, let's say I'm looking at the world and I know that things are placed in a certain way. So my brain, let's say, takes this input in a different way, but it doesn't mean that I have to perceive it exactly how it is on my retina. It goes into the brain, it gets processed by the fact that I can reach for it and it's on my right side, I know it's on the right side, right? Later brain area process that in the right spatial place. Does that make sense?
Kind of, it's just challenging, like gravity. Like how I'm specifically thinking of like the vertical flipping, like how are we not experiencing the world?
We process it correctly without flipping it back. That's what's.
Yeah. So you don't have to flip anything back. Again, the idea is that there is this idea that just because it's flipped in your eye or flipped in the brain, that doesn't mean that you have to perceive it that way. Perception is not necessarily tied to how your eye represents it. Does that help? I don't think that helps. I'll explain it a little bit. Yeah, but it's a more philosophical issue in a sense that I think a lot of time perception is more about differentiation rather than it's about how exactly it is on your brain, right? So you're differentiating different perception. As long as they're different, your perception can correct for it. I'm not helping. Later on. Okay, all right. Okay, let's look at the information that comes from the left visual field. So when the information comes from the left visual field, it falls on the nasal side of the left eye, and it falls on the temporal side of the right eye. It should be obvious, right? Really, because it's a lens, and then the information goes and falls on that side. So in this case, the information from the left eye, which is from the nasal side, has to cross over to the right side of the brain. And then in a place called LGN, lateral geniculate nucleus, the information gets integrated. And then it goes back to the visual cortex. So the visual cortex, so pay attention to this, where it is. It is in the back of the brain, and it's kind of in the inside, in the back of the brain. It's not on the outside. As I said, this is a slice of the brain this way, and it's in the back here. Optic chiasm, this is a place where the axons from the nasal retina cross over. So the nasal part of the right eye and the nasal part of the left eye cross over in the optic chiasm in order to end up in the place that they would be processed. That's why if you have damage to left hemisphere, you're maybe blind to the right side, right? So this should explain some of those things that you've heard about. See, optic chiasm placed in the visual pathway where axons from the nasal retina cross over to the opposite side of the brain, and axons from the temporal retina stay in the same side. So the temporal part of the right eye stays on the right side because it is getting input from the left visual field, so it doesn't have to cross over. Okay. this pathway going from the eye to LGN to the primary visual cortex. Primary visual cortex, some people call it the striate cortex. So that's why this pathway is called the genicular-striate visual pathway. It connects the retina to the lateral geniculate nucleus, or LGN, and then the LGN to primary visual cortex. When I call something pathway, what do you imagine? What does it mean when I say something's a pathway? A highway? Yeah. No, metaphorically, yes. But in the brain, when I say this pathway or that pathway, what would that mean? Yes? You gotta speak louder, say that. Lines of nerves next to each other. Like a what? Yeah. Okay. So there are obviously long nerves, and nerves are really these bundles of axons, right? They're not anything special, right? The axons that we talked about, you bundle them, and then that's what a nerve is. Does someone want to make a comment here? Yeah. Connections between cells, right? A pathway is not just axons. It's really multiple stages. So you have a set of, let's say, photoreceptors. They get the light, they change shape, they have a certain activity. That activity releases neurotransmitters in a different, amount to the next stage, and there are cells there, and it causes a certain activity there. Those release neurotransmitters differently to the next cells through their axons, and those will have a different patterns, and then those. So that's what the pathway is. It's not just one long axon from one end to another end. It's really this patterns of a cascade of activity that gets pushed down stage by stage, right? Depending on the activity in the first stage, you have a different neurotransmitter release in the next stage that causes a pattern of activity, Yeah.
So about the like activity of player.
Yeah. Yeah. So I talked about computation in the last module a lot. In the brain, when I talk about the pathway, where is the computation? Excuse me. Where is the computation in that pathway? Yeah, right? Well, how do connections are computing? The what? The hidden layers and yeah, but how are the connections computing? Like, what does it mean that the connections are computing? I want to know what you took away from the first module.
The presynaptic cell, whether it's inhibitory or excitatory, and then what's the third factor? What?
With connections?
Yeah, the connection. The synaptic.
Yeah, so let's consider a physical system. I want to know, like, I want to give you some intuition about computation. How does a scale work, like a mechanical scale or a scales that they weigh? If two people, let's say, I'll explain that. So let's say a scale, like I'm trying to see the weight of something, or two people, they stand on a scale, and let's say the scale is a system that it's a hydraulic scale. A hydraulic scale has some liquid in it. When somebody stands on it, they push the liquid down. That pushing of the liquid down pushes up a gauge, and then you see what the weight is. I could describe the behavior of that system as if it's computing the sum of the weights of two people that are standing on it, right? It's a mechanical system. Does that make sense to everyone? Computation is not always a property of every single component. computation is something that how you describe the behavior of a system. So you could have a mechanical system, and you could say, well, this mechanical system is computing the sum of the weights of the two people standing on it. Another example of a scale, let's say you have a scale where it's electric, where let's say there's a device in it, you stand on it, it pushes the device down, it changes its resistance, you pass electricity, and then based on how slow the electricity or how much resistance there is, you measure the weight. So these are mechanical systems that are computing something, right? So computation is a way of describing the system. When I talk about a pathway, this pathway is computing something. How is it doing? Well, you have activity that is caused by light in photoreceptors. That activity releases neurotransmitters, and those neurotransmitters cause another activity in the postsynaptic cells, because the postsynaptic cells just are active based on whatever, inhibition or excitation they're getting from presynaptic cells. But that process is computation. That process of releasing neurotransmitters based on the weights that are there, it's computing something, because the patterns mean something now. If there was, depending on what the pattern of light was, there's a different pattern in the postsynaptic cell. And those postsynaptic cells cause activation in postsynaptic cells. So the behavior of that system could be described as if it's computing something. But think about those mechanical systems, and what do we mean when we say they compute things? They're not computers. They don't have chips and transistors or anything in them. But based on their physical properties, they can compute things. They can give us information about something. All right, that's enough about pathways for times. Next. Okay, let's take a 10-minute break. 6:53, 7:03, we're gonna. Okay, so this pathway is called genicular striate visual pathway. There's another pathway that is smaller and much more evolutionarily older, where it connects the retina to the area called superior colliculus, and it's involved in eye movements and actions, and that pathway, we'll talk about it in a little bit. Today we're gonna spend a lot more time on this pathway and talk about how visual input gets transformed from one stage to another stage. This pathway, as I said, is much newer because it connects to the cortex, and cortex is much newer, structure of the brain, newer like in evolutionary time. And it does a lot of the recognition and pattern analyses and all those sorts of things happens in this pathway, right? Just a matter of terminology, these projections that go from the LGN to the primary visual cortex called optic radiations. It's just a lot of nerve that just projects, and then this figure tries to show it to you. It's a lot of nerves that get projected down to the LGN. So LGN, this is the first stop in the brain after the nerve fibers are leaving the eye. As I said, there's a crossover to gather the information that comes from one visual field into the opposite side, LGN. So LGN on the left hemisphere gets information from the eyes about the right visual field. And the color coding here just to show you what visual field they come from. It's not in the nerves or in the visual world. It's just the color coding. This information comes to the LGN. The LGN is bilateral. It means that there is one of them in each hemisphere. It's not, which would make sense because it has to gather information coming from the opposite visual field. the response of the cells in the LGN is the responses that we saw previously, right? We saw these responses that are center surround antagonistic. And this is very similar to also ganglion cells. The ganglion cells that are in the eye, those cells also have similar response. So there is not a lot of computation happening. This connection is mostly carrying information from the ganglion cells to the LGN. So we have this response, for example, and based on this response, imagine this gray area is light. When you look at the response of this cell, is it a center surround organization? So is it on center off surround or off center on surround? It's on center off surround. Why?
Causes more action potential.
Yeah.
When it's on the side, on the surround, causes fewer.
Yeah, so increasing the size of the light in the center area increases activation. When the light goes into the surround area, it starts inhibiting the cell again. Each of these lines is an action potential. This is one way of displaying action potential, which is you just show all of them, and based on how many of them there are, you know the firing rate was higher or lower. This is just light. Achromatic always means that there is no differences between wavelengths. This is a center surround organization because, well, the center and surround have opposing effect. So that it would be a center surround, antagonistic, and it's center on, surround off. So that's the response of the cell that you would find in as a ganglion cell, which is in the eye, which I didn't get too deep into it, but these are ganglion cells. The ganglion cells are the ones whose axons are leaving the eye and create the optic nerve. So this would be a response of a ganglion cell, the center surround antagonistic organization. As we said, you could have on center off surround or off center on surround cell, which is just the opposite of what we saw. And there's also there is what's called on off. So and the response is something like this. So what is this cell responding to? Okay. So imagine this is the stimulus. The light comes on at this point and then it goes off at this point. So the on response is when you have a stimulus, it's on, right? When they're coming. The off response is that when you have no stimulus, the response is higher. How about the on off? What is it responding to? When we ask what is it responding to in the behavior, what does it mean? It means that when is the activity, the firing rate is higher? Yeah.
So activity rate seems to go up whenever the stimulus either turns on or off.
Yeah, so it kind of responds to change. So there are cells that only respond to change. So when the stimulus comes on, they fire a lot of action potential, but when it stays on, they go down again. And then when the stimulus turns off, this change again causes them to have a higher firing rate. And then when it's off, it goes down again. So they're really just, change detection in a way. When there's a change, they fire a lot of responses. When there's a change in the receptive field, then when it stays the same, they also go down. So they're change detection. They call them on-off cells. So let's see. Yeah, we talked about these sorts of receptive field where as I said, you have on center, on this side you have off center, on surround, and this you have on center, off surround, off center, on surround. Okay. Okay, so an important topic in the brain is what we call retinotopy. Retinotopy refers to the fact that information that are close to each other in the visual world are processed by neurons that are close to each other in the brain. Okay, so what does that mean? That means that, let's say this is the visual cortex, and let's say you basically lesion a specific area of that. That lesion causes blindness in the visual world. If you now spread this lesion, you see that the blindness also spreads around the original point. Said differently, if I take one cell and I find its receptive field, then I move my electrode a tiny little bit and I find the receptive field. The receptive field of the second cell is going to be very close to the first cell. Does that make sense to everyone? Right? Just moving the electrode a little bit is not going to completely move the receptive field. Do you see how these two, the way I'm describing it on this slide and the way I described it, are the same thing?
Yeah.
Okay. So I'll define the retinotopy again. So in the eye, let's think about on the eye. It all starts in the eye, and we call it retinotopic because it maintains the organization of the retina. So the light from this tip of this pen is falling here, or let's say from the other end. The light from this end of the pen is falling here. The light from next to it, it's falling next to that point, right? Does that make sense to everyone? So when the light is coming from nearby location in the world, it falls on nearby location in the retina because that's how physics are, right? It's right next to each other in the retina. Those projections go into the LGN and then they go into the primary visual cortex. And what happens is that those receptors that are next to each other in the visual world end up connecting to the same cells or very nearby cells in the visual cortex. So if you look at the receptive field of one of those cells and it's connected to these photoreceptors, its receptive field will be this part of the world. If you look at the neighboring or a nearby cell, it's connected to nearby photoreceptors, so its receptive field will be nearby. Does that make more sense? Yeah, I'm not getting a lot of feedback today in terms of, I don't know if you're all lost or this is all very clear. Okay.
So different, something for minds, and, so, the brain, like, good validation of the brain, the guy, the lens, let's say, is compromised, and that's why we treat the lens in order to have a better image. If we have a lesion in the brain, we have to treat the brain with that.
I'm not following your question.
I'm trying to connect the input and output thing. So I understand right now. There's could be an issue on the input side or an output side. So I understand.
So no, I'm not sure if that's related to retinotopy, but let's just stay with this. What I'm trying to say is that do I have figures for this? Let me. Okay, is this too much of this one? Okay. So let's say you're looking at this figure. Okay. This is the right eye, this is the left eye. Right, left. If I'm looking at this figure where there is a square and there is a triangle, and this is the fixation point right at the center, what would happen? Well, I said that the visual input is flipped horizontally and vertically, right? So this square, which is on the, because this is the fixation point, this is in the upper left quadrant, it gets projected into the right eye in this area. It's kind of flipped horizontally and flipped vertically because there's a lens and this area gets to the lens and it comes here. The visual, so this square activates neighboring photoreceptors because the light is coming from nearby location. Does that make sense to everyone? Because the light is coming from neighboring locations, it would activate neighboring photoreceptors. The question is, would it also activate neighboring cells in the primary visual cortex? That's what retinotopy would be. That this organization is maintained as you go into the visual cortex. That because the neighboring areas are active in the photoreceptors, it happens to be the case that the neighboring area also in the primary visual cortex would be activated because you're maintaining that organization. You're maintaining a map of this space. Yeah.
I have a question about focal points. It's interesting that in this image, each eye has a different focal point, and there's like two images, and I'm wondering, like, as I look at it, I'm having a hard time, like, having two distinct focal points between my eyes. I don't know if that's like the difference or the distance to the screen, but I'm wondering, like, do your right and left eye ever share a focal point? I don't know if my question makes sense.
So no, this is just a visualization. So you could have different, so the input to the two eyes are slightly different. But you're focusing with both of them at a certain location. So when you're
Often your eyes do have the two different eyes can have one shared focal.
the focal point is in the eye, right? So let's say, what's that?
I understand that.
So yeah, so if I'm looking at something, the focal point falls, if I'm focusing on something with the two eyes, the focal point is in the eye, meaning that the point that all the lights gets converged is on my fovea.
The focal point isn't the stimulus itself.
No, so the stimulus could be where you fixate. And if you fixate, it means that you're letting the input from that stimulus hit your fovea. So if I'm fixating on the HP on this mouse, I'm letting these, like the light being reflected from this area hit my fovea. The focal point would fall on the fovea, like it's where the lens is converging all the light. Yeah. This is just a visualization to show, okay, the input to the two eyes are slightly different. And the reason being, well, they're at different places in the world, so they look at things differently. And that's an important thing, right? Why is that important? What is the use of the fact that we have two eyes and they have a slightly different input? Correct each other, okay? Depth perception, right? When you want to have good depth perception, it's good to use two cameras, right? Because when you close one eye, you look at the world, you look at, like, if I have something in front of me and I close one eye and I look at it, so the input changes. And that discrepancy that you get from the two eyes can give you a lot of information about depth, right? If it's really close to you, it's a higher discrepancy. When it's really far from you, it's a lower discrepancy. So a lot of depth perception depends on the fact that we have two eyes and the input is a little different. So back to retinotopy, I think it kind of makes sense, right? That the visual inputs that are close to each other in the world would activate neurons that are close to each other in the brain. That's all it means. Now, that means that if you make a lesion in the brain and you make a lesion next to it, then you're going to see cuts in the same areas of the world because they're processing the same areas of the world because they're close to each other. I don't think it's a complex topic, right? It's just the fact that in the retina, close by physical locations activate close by photoreceptors in the retina, and then those get projected into the primary visual areas. The important thing is that the brain maintains that map. It doesn't jumble them.
So the bigger the lesion in that area, bigger the like obstruction.
Yeah. Yeah, I mean, so if you're an adult and you have a lesion to certain part of your primary visual cortex, you're gonna see a black cuts in the wall. Like you don't see like a black thing like this. It's like as if, right? As if it's completely dark. When the lesions are closer to the sensory input, they're more visible in a sense, right? If they're higher up, they manifest themselves in different sort of, I guess, what's the right word for it? They manifest themselves differently, but when they're closer to the visual input, you see them. You're aware that there is a hole in your visual space. And if they're bigger, yes, because you're losing visual information from a bigger chunk of the world, so you'll see it as a bigger whole. That's a requirement. If it's retinotopic, it has to have that property. Okay, let's see. So after LGN, we looked at LGN, and this is the area, lateral geniculate nucleus. This is the area that, as I said, it's the first stop in the brain. This is not a cortical area. The cortex is above that. And when you get inputs from the two eyes to the LGN, that inputs get projected into the visual cortex. The LGN, we talked about it, it's a bilateral structure, and it's very small, but the primary visual cortex, which is in the back, V1, is much bigger than LGN. LGN is a old, like evolutionary older structure, and it's small. So let's continue building some intuition for what retinotopy is. All right, let me find a good picture here. Okay. So when you look at the brain, it looks something like this. And I know you all probably took the anatomy crash course from Kate. But I'm going to talk about it a little bit. So when the brain looks like this, what you see on the surface, that's the cortex. And it's kind of, when you take it out and you open it up, in reality, it's just the size of a large dinner napkin. And it's about the same thickness, right? The cortex is a surface that is maybe a few millimeters thick. And it's like, as I said, it's like a dinner napkin. But when you put it in the brain, in the skull, you have to bunch it up, right? So if you, let's say, this is the brain, this is the back of the brain, this is the front of the brain. If you slice it this way, this is what you see. The surface on top, that's what the cortex is. That's what the large dinner napkin that I'm describing is. And it's really just a few millimeters thick. That's where the neurons are. All the other areas here, these are connections, right? The cells are connected to each other, all these axons. But the cortical areas are really on the surface of this. You can imagine, again, this is what it looks like in the back of the brain. So if you make a cut here, this is what it would look like. the surface are where the cells are. So you could imagine you could blow this up, right? So this is this the right hemisphere or the left hemisphere? What's that? Somebody else? It's the right hemisphere. Why is it the right hemisphere? Like, is it? I mean, I don't. You guys haven't seen brains before. What is your exposure to brains? None. Okay. So let's see. How can you tell? Like here, how can you tell if I'm looking at the right? What I'm seeing in front of me is the right hemisphere or the left hemisphere? What's that? From the what? Yeah, so what I'm looking at, what hemisphere am I looking at here? The left hemisphere, right? Because this is the front, this is the back of the brain. Now, when you could see this area, it means that, what am I looking at here? The inside of the right hemisphere. Why? Yes, so if I take this brain and cut it not in this direction, but perpendicular to it, it means that I'm dividing the brain to two hemispheres. The one that is in front of me is the left hemisphere, and if I get rid of that, what I'm left with looks like this, which is the right hemisphere, but I'm looking at it from this angle that I'm looking at this one. I'm looking at it from this angle, I cut the left hemisphere, got rid of it, what I'm left with is the right hemisphere. Here, so this side is what hemisphere? Why is it the left? Where is the back of the brain here? This is the back of the brain. We're looking at the right hemisphere on this side. Okay. So this deeper than I thought. Okay. Okay. Maybe I'll do some anatomy next week just so you have some more understanding of this. But the takeaway, so let me do just a little bit now so you have some better ideas. So what is this area called down here? Cerebellum. So a lot of time when you look at the brain, there are multiple things that you could look at to tell you to orient yourself. One, this is the brain stem, right? The brain stem is going, when it exits the brain, goes toward the cerebellum and then goes down. So based on the direction of the brain stem or based on the position of the cerebellum, you should be able to know that you're looking at which side is the front of the brain. Another thing is the fact that where the temporal lobe is, right? The temporal lobe goes from the back of the brain toward the front of the brain and it just bends down, right? So this is the temporal direction. Also, can you look at the connections, which is the corpus callosum, which is the connections between the two hemispheres? That's also another thing. When you look here, this is the connections between the two hemispheres. Here, you're looking at it right here. You see, everyone sees this? So when you look here, well, the cerebellum is not here, the brainstem is not here, but what is here that can tell you that this is the back of the brain? The temporal lobe is here and is pointing in this direction, right? If it's pointing in this direction, it means that this is the frontal lobe. This is the occipital lobe where the visual cortex is. And this, the line here, is the line between the hemispheres. So this area up to this point is the right hemisphere. This area is the left hemisphere, and you don't see the rest of it. Let's come to this now. Which hemisphere is this? The right hemisphere. Why? Which angle are we looking at it? So you can imagine that I look at this. Okay? If I now take this and then move it a little bit in this direction, you get this, right? So we were looking at it from this angle. Now I just took it and then rotated a little bit, because this is what it looks like from this angle. When you look at it from the inside, it looks like this. This is the back. This is the temporal area that is going downward, and then that would be the front. And this would be the connection between the hemispheres. So this is the right side, the right hemisphere. The difference is that it's now blown up. When you look at the brain, as I said, it is completely wrinkled, and these wrinkles, these are these sulci and gyri. Why are they there? Yeah, so because it would have to fit in the skull. It's too big, so you're just gonna jam in it in the skull, and what happens is that you just get folded, right? It's like when you have a big dinner napkin and you're putting it in your pocket, right? It gets, folded in different places, and that's what is happening here. In reality, it's just the surface, and you could blow it up. You could put air in it, metaphorically. And when you put air in it, the right hemisphere would look something like this. This is the back of it. This is the temporal lobe that is going down on the right side. And then this is the front. And this would be where the corpus callosum is. This is where the right hemisphere would connect to the left hemisphere. Does everyone see that?
Is that from the bottom?
Yes. So it's not exactly bottom. It's like, a little, yeah. So you're not looking directly at back of it. You're looking at, at angle. The exact angle of it would be something like, as I said, so this is on the side, right? So imagine somewhere between side and back, and then from below. Yes, that's how it's being displayed here. This would be where the visual cortex is. Does everyone see that? Yeah? So here, for example, so this is the front of the brain. As you see it, it should just be obvious to you at this point. This is the front, this is the temporal lobe, this is the back of the brain. If I take a slice like that, the stuff that are really close to the surface, that's where the cortical areas are. They're very close to the surface. You go a little inside, you're hitting the nerve cells that basically the connections between these cells. But on the very surface of it, that's where the cells are. And the areas are practically just patches on that surface. When we talk about V1 or V2 or other areas that we're going to talk about, any brain area, if it's a cortical area, it's just a patch on that surface. So when I was showing this, you could see that here. This is a slice this way. And what you see is that the cells are at the surface, and then the inside of it are basically, as I was talking about. For example, these are the optic radiations. These are axons of the LGN cells connecting to the primary visual area. So all this area in the middle, they're just axons and other stuff that happens in the brain, like veins and all those sorts of other stuff. But they're not cortical cells. The cortical cells are all close to the surface. Okay. Is this the right hemisphere or the left hemisphere? Who said left? Why would it be left?
Oh, I thought.
No, just joking. So this is what hemisphere? Why is it the right hemisphere? Yeah, so, and how are we looking at it? So it is cut, right? You see that it's cut? So this is when you can see this white thing in the middle, how is it cut? Right? So somebody's coming technical term. So this is cut. Pictures here. This is cut like this one. So you take this and then basically perpendicular to this, you cut the two hemispheres from each other, and then you get rid of them, and then you could look at the connections there. So here, this is the right hemisphere, and you're looking at it. So this is my right hemisphere, and you're looking at it from that angle, right? You all see that? That's why you could see the connections. You could see the back of the brain, and the temporal lobe is here. This is the left side. No, this is what? This is also the right side. This is the right side also, but you're looking at it from a different angle, right? So you're looking at the right from this angle. Clear? Now the visual cortex is back here. When I'm looking at this figure of this face, the left side of this face, the left side of this image would fall on the right hemisphere. And it would be in this area. Yeah.
My bad. So one that you're pointing to, right? So it's cut in half. Is that the left side of the brain, but you're looking at it from the right side? Am I wrong?
No. So this is, when you look at this, you could see these connections. This white area is the connection between the two brain hemispheres.
That's the middle of it.
Yeah. So if this is the middle of the brain, it means that there was the other side of the brain was in front of it.
Okay.
And which side is the front of the brain? Which side?
You look at it to the right, or am I wrong?
No, this is the back of the brain, right?
Oh,
This is the front.
okay. All right.
So let me,
That makes sense.
does it make sense? So so imagine this is the right hemisphere, but you're looking at it from this angle, and then you got rid of the left hemisphere to see what's going on in the right
The orange
hemisphere.
part is the cerebellum.
So cerebellum would be below that. The orange part is part of the cortex, so it's the occipital lobe. Yeah, so I'll go back to this one. So here, when you could see this white area, it means that you cut the brain, not the way I'm showing here, but you cut the two hemispheres from each other.
Is that thing at the bottom of the brainstem? Like in the bottom left corner,
This,
on diagram A.
here you mean? No, this is the temporal. Am I missing?
My bad.
Yeah. No, it's okay. It's okay. So it's good for everyone to get some intuition of what the brains look like, and when you look at it, you have to have a general intuition of what you're looking at. So again, I'll do some 3D visualization next time for you to get a better sense, but you could do it yourself too when you go back home. Just look at different brains and see what the 3D organization is and what cues you can get in order to see what you're looking at. But this is, as I said, this is the right hemisphere. This is the back of the brain. Because you could see the connections between the two sides, it means that you cut it, the right hemisphere, you got rid of the left, and then you could see it like this. Okay, let's look at this instead. This is the right hemisphere. This is the temporal area. Parietal up here, occipital back here, frontal in the front. Now, if I'm looking at this image, imagine this is my image. This is more of a visualization. What you could see is that the areas that are closer to the fixation, this where imagine the middle of it is where you're fixating. The areas that are closer to that fixation would be visualized closer. You see what I mean? As you get farther out, this is what retinotopic organization is. Does that make sense to everyone? What retinotopic organization is? The areas that are close to each other in the visual world are represented by close by areas in the surface of the cortex. So if you're looking at a face, this is a schematic. If you're looking at a face, the areas that are representing that face would be close to each other. So meaning that the areas that are representing the eye are close to the areas that are representing the nose because they're close to each other in some ways, versus areas that are representing the hair. Does that make sense? These are schematics. They're not real visualization of what the response is, but it's just projecting it there to give you an idea. So, all right. Let's see if I could. Okay. Is this the right visual field or this is the left visual field, right? You can all see that. So because it's the left visual field, it would be projected to the right visual, right cortex, right visual cortex. And then you could see it here. Are you seeing, okay, does it make sense what I'm showing? Are there any questions about it? Yeah.
So the type of signal that each area of the image will trigger in the brain, maintain that structure in the brain.
Say that again.
Whatever image we're looking at.
Yeah, so yeah, so yeah, that's correct. So when I'm looking at, let's say this was the image, and in this graphic we're showing that the input from this part of the visual field is processed by this neuron, this area in the visual field. Does that make sense? So we're saying that the blue areas are processed by these neurons. The red or brownish area is processed by these neurons. So the areas that are close to each other in the visual field are processed by close by neurons in the visual cortex. That's the idea. What do you see here that may be surprising? The shape is distorted. In what way is it distorted?
Like red part is very small, but
Yeah, yeah. So this is what's something that's special about the fovea again. The point that you're focusing on gets magnified in the visual cortex. So a big part of visual cortex is dedicated to processing information at the fovea, and we call that foveal magnification. Versus the periphery, which gets kind of squished, like a relatively much smaller cortical area is dedicated to processing the peripheral visual input. And that's why, again, we're very good at foveal vision. Tissue, like there's something, and we talk about, when we talk about attention, we talk about this. Visual input really fight for being represented. And what that means is that how much of the brain neurons are being dedicated to different visual input. And fovea gets a big chunk of that, like they're being represented by a lot of cells. So as I said, there are two important points here, foveal magnification, but also retinotopic mapping, that areas that are close to each other are represented by close by. So in a way, when you're looking at an image, it's being reflected in your visual cortex with the same organization. You're not going to jumble it up. You're going to have the organization maintained. Okay, the primary visual cortex also is a layered structure. So when we look here again, this is the surface of the cortex. And I'm going to finish it on this one. I'm not going to go further, but this is the surface of the cortex. The V1, the area V1 that we're going to talk about, and other areas, V2, V3, these are just chunks. Like imagine this is a large dinner napkin that is shaped that way. It was bunched up. We blew it up, so it's a surface. Now every cortical area, every brain area in the cortex is really just a little patch of that dinner napkin. That's what in reality it is. It's just a little area in a napkin. It's a layered, and we're going to talk about it, but it's just a little area. So V1 is a little area, V2, V4, different areas are really just, I mean, they're patches of neurons, but in the case of cortex, they're really just on a two-dimensional surface. And we're going to talk about the properties of V1 next time. Spend a lot of time today talking about anatomy. But you should all do this homework. You should, you know, we have a homework, but also just to spend some time looking at brains, looking at brain anatomies and like 3D visualizations. Just get a good sense of what brains look like from different angles. Just it will help you in this course and also in the future. All right, I'll see you all next week.
Did anybody not find